Hi, good day everyone. Today our company TSG Laser Scan Groups would like to share some experience and output throughout our study regarding the UTM's remote control circuit. Before start the sharing sessions, let me introduce our key people in the company. And this is the VIP, very important people of our company. Okay, let me introduce one by one. For our company, which consists of 7 members in our teams and led by our Chief Executive Officer, CEO, Dr. Susanna, and the other 6 members are Ms. Charmin, Mr. Hammerling, Mr. Nelson, Ms. Chai, Mr. Wong, and the last, our project manager, Mr. Heng. Now, let us start with our sharing sessions. This project is one of the first to use the LiDAR technology to scan the RC track in 3D with excellent precision. The goal is to make sure that the preserving is done correctly and to study the structurals. RC racing is much better now that is used the systematic laser scanner and modern software for data processing and mesh corrections. In addition, this tool is making it easier to do the further research and maintenance work. For the problem statement, if we don't have the enough 3D of RC racetrack, make it hard to do the maintenance work and complete the structural analysis. Conventional technique may be expensive and inaccurate, so it's important to use the new technology to find the secret flaw. Alright, so the next, we will further discuss the aims and objectives for our study. This project aims to use the terrestrial laser scanning technology for precise data collections, generate an accurate 3D model of RC racetrack, and to analyze the structural deficiencies to inform the restoration decisions, and ensuring through the assessment for maintenance needs. In order to achieve these aims, we have come up with 3 objectives. So for the first is to capture detailed 3D scans of the entire race car tracks to document its current state. For the second is to create a comprehensive digital model for preservation and further analysis. And the last is to identify the structural integrity issue, if any, for potential restoration consideration.
Next is the project planning. The project planning consists of our study area and the instrument that being used along this project. For the study area, our study area for this project is located near the alumni house, which is the UTM RC track. There are 3 main instruments that being used along this project. First, the Topcon GLS 2000. It is to scan the RC track. Next, the Topcon GR5 to establish our ground control point. Lastly, the prism as a reflector.
So now, I will present the project milestones. Here is the grand chart of our group projects. So, for the project plannings and site recognize is done in week 1. From week 2 until week 3, our groups conduct laser scanning data collections following with the data processing. After finish the data processing, results and analysis is done in week 3 to week 4. And lastly, reportings and final presentations is done in week 4. In session 4, I will talk about the overall flowchart of our group project. We start our project with the project plannings, defining scope, conducting a site recce, estimating project durations, and setting resolutions. We start our project with the project plannings. Moving to the data acquisitions, we perform fieldwork using GNSS for accurate location data and employ scanning for detailed site information. The collected data undergo registrations, georeferencing, and data filtering. the collected data underscore registrations. At data processing phase, we're using magnet collect and crowd compare to process our data. At data processing phase, we're using magnet collect and crowd compare to and finally, we generate a detailed 3D models as visual representations of the site.
Okay, so before we start our data collection, we perform a site recce to determine the amount and the location of stations we need for this project. So after the site recce, we have decided to use a total of 9 stations. Before we start scanning, we also use assumed coordinates before we start. First, we observe from station 1 to station 9 first to obtain the coordinates of its stations. Then, we start the scanning from station 1 to station 9. Lastly, we export the data from the TLS for further data processing. And for the GNSS observation, our base station is located at the helipad, and we choose Station 1, Station 4, and Station 5 as our control points. And the GNSS data is exported for further processing to obtain the coordinates and the elevation of the control points to replace the assumed coordinates that we have used before.
After Wong have explained the data collection, now we go for the data pre-processing. Data pre-processing are divided into 3 stages: registration, georeferencing, and data filtering. The pre-processing software that we are using is Magnet Collage. After we open up Magnet Collage, then go to File, then click New Workspace. Go to the blue laser scanning icon above to add scan project. Then select the file that are in PRJ format. Click User Define for the specified coordinate system. Then double click on the file name, which is TLS RC track 13, 12, 23, and the 2D point cloud for the RC track are displayed. Right click on the folder name, which is TLS RC track 13, 12, 23, and click on the process scan and image. At the part post scan, click Start. At the left window, click Primitives, go to Points, and insert the coordinate east-west elevation for station 1, 4, 5, and 8 that have been processed in TBC for georeferencing. Go to the left window and select the first station. Then, at the right window, double-click each station, occupation and backside registration to confirm the traverse. Click Report and check the value. Residual Z and value that are more than 0.005 need to register again and recalculate. Repeat this step for each station. Click Cloud and Polygon to select the unwanted data. After the selection, click Delete to remove the unwanted data. Continue to do the data filtering process. If the unwanted data are large, method below can be used. Click the area that needed. Click Invert, then you can shift the selected area as below. Select Delete to remove the unwanted data. Continue the process till the data are clean. This photo shows the point cloud of the RC track after the data filtering. Next, open a new folder which includes model and export. Click the file and select Create New Model Project. Choose the folder model that have been created. After that, right-click New Model, and select the point cloud. Lastly, click Start. Click the new model and export it in LAS file format. The data are further processed in Cloud Compare. Next stage, we are doing data processing. Data processing includes meshing and generate 3D model. The processing software we are using is Cloud Compare. After we open up the Cloud Compare software, go to File, Open. Choose the LAS format file that have been processed from the Magnet Collage software, then select Apply All. For the global shift and scale, select Yes to All. Then the 3D point cloud have been imported into the Cloud Compare. Select Edit, Normal, then Compute. Choose Triangulation and then select OK. Next, we are going to Plugins and then choose Poisson Recon. Set the value 10 for the octree depth, take the output density as SF and then press OK. Then the result will be shown like this. Go to the window properties, adjust the display range until the model is nearly shaped. Click Edit, Scalar Fields, Filter by Value. Based on the default value, click Export. Go to the window properties. At the color section, we select RGB. After the selection, the true color of the RC track is displayed. Click Edit and select Mesh, then select Smooth Laplacian. Both of the pop-up window follow the default value, and click OK. Lastly, this is the result of the 3D model of the RC track in Cloud Compare.
So based on the slide, that is our final outcome for our project at remote control track. There are 4 discussions that we managed to come out when we conduct this project. The first one is 3D model accuracy evaluation. The 3D models generated through laser scanning demonstrated a high level of accuracy in capturing intricate details of the race car circuit. The precision achieved in recording the track's geometry and surrounding structures allows for a comprehensive representation of the current state. The evaluation of accuracy is vital for ensuring that the digital models faithfully reflect the physical attributes of the race car track. The second one is structural integrity analysis. The 3D models were utilized to identify potential structural deficiencies in the race car track. By analyzing the point cloud data, anomalies or irregularities in the track surface and structures were detected. The information served as a foundation for informed decision-making regarding restoration and maintenance. The ability to uncover hidden structural flaws enhance safety measures and contribute to the long-term sustainability of remote control race car circuits. So the third discussion that we managed to come out based on the result is georeferencing of 3D point clouds. The process of georeferencing 3D point clouds was successfully executed using ground control points and GNSS technology. The establishment of GCP around the study area, coupled with precise GNSS observation, ensured accurate spatial referencing of the point cloud data. This georeferencing step is crucial for integrating the 3D models into the real-world coordinates, enabling effective collaboration with geographical information systems. And the last discussion that we managed to point out is mesh creation and texture mapping. The final stage of the project involved creating a mesh and utilizing texture mapping to generate a realistic 3D representation of the race car track. This visually appealing output not only enhances the remote control racing experience, but also serves as a valuable tool for future study and prospective repairing projects. The mesh creation provides a tangible and immersive visualization of the track, contributing to a more engaging and informative analysis. There are 2 limitations that we managed to find out when conducting this project. The limitations are scan resolutions and weather conditions. For the scan resolutions, the chosen scan resolution is 13mm over 10mm accuracy may introduce limitations in capturing extremely fine details. Consideration should be given to employing high-resolution scanning techniques in areas where precision is important. While for the weather conditions, such as heavy rain or fog, can impact the effectiveness of laser scanning. Future projects should take into account for weather-related challenges and implement suitable measures to mitigate their effects on data quality. There are 3 resolutions that we would like to recommend when we encounter problem statement and limitations when conducting this project. The first one is enhanced scan resolution. Explore the feasibility of utilizing higher resolution scanning options to capture finer details, especially in critical areas where a higher level of precision is required for structural analysis. The second one is continuous monitoring. Implement a continuous monitoring system for racing car circuits using laser scanning technology. Regular scans can help detect subtle changes in structural integrity over time, enabling proactive maintenance and minimizing potential risks. And last one is integration with maintenance protocols. Integrate the generated 3D models and analysis results with existing maintenance protocols. This ensures that structural assessments are seamlessly incorporated into routine maintenance practices for more effective track management. So, by addressing these limitations and implementing the recommended measures, future applications of terrestrial laser scanning in remote control racing can further advance the accuracy and utility of 3D models for both preservation and structural analysis purposes. In conclusion, laser scanning technology has transformed remote control racing, providing precise 3D models for enhanced safety and sustainability. Despite limitations, our recommendations pave the way for ongoing improvements, establishing a foundation for informed decision-making and continuous maintenance. This technology ensures a secure and immersive racing environment. That's all from us. Thank you.